All right, I want to say something about slope stability. It's something we look at slope failures quite a bit, but we don't really put numbers on them. So I want to show you how you can put some numbers onto some situations. So let's take a look at this common situation, which is that we have bedrock with a wedge of soil sitting on top of the bedrock. Now this is common because, you know what, we have a mountain here or something like that, and we have soil sitting on the top of the mountain or the side of the mountain, and it could slide. So we're interested in determining what is the stability of that particular soil wedge. This problem ends up to be pretty much identical to the problem you did in statics, which is a block sitting on a plane and determining whether or not the block is going to slide down the plane. So if you recall statics and your block sliding on a plane problem, how did you analyze it? Well, you did a free body diagram of that block. And how did that free body diagram look? You had a W going down. You had, you simply had a normal and a shear, or we called it a normal force and a friction force. And if you remember, F is equal to mu times N. That is what is resisting the block from sliding down, and what is pushing the block down ends up to be W sine alpha, where alpha is the angle of the ramp there. So if this is greater than that, it's going to slide. On the other hand, if the resistance is greater than that, then it's not going to slide. So it's the same problem, but a different geometry. So that's what we're looking at is the same problem as this block on a ramp, but you can see there's some geometry involved there. That's basically all there is. We need to get the W for this wedge here, and that can be done. But we end up with, again, the force down the ramp. So if I take a free body diagram of this, again, I end up with, the weight, and, the weight has two components, one that's perpendicular to the slope, this angle here, the ramp, and the other one that's parallel to it. So we break it down into those two, just as we did. Well, I guess I didn't show it over there, but again, the force down is the W sine alpha. Okay, but now, so this is the geometry that we're going to use here. We have this is our bedrock, and this is our soil wedge, and we define some terms. We have this H here, this is the base of the hillside, and that's H. D is from the bottom of the wedge to the top of the hillside. And we have this length here, which is the distance that it's in contact with the bedrock, the soil, and so and then we have the angle beta. And we're not using alpha here now; we're using beta. That's the angle of our slope there. This one is alpha, similar to that one. So I'm not going to go through, it's just geometry. So, and then we have this little h here. The little h is this little distance, perpendicular distance from the slope to from the rock to the top of the soil. So it's just geometry. We're not going to go through it, but this is the equation for that small h. This is the equation for the W. This is the equation for the L, and this is our force down, the W sine alpha. This is our resisting force. Now, that's where the soil type comes in. So this is where when you're in practice, this is what you have to worry about the most, in a sense, that you got to get the soil strength right. This SU for the clay undrained that we talked about, so it's SU. For the sand drained, then you got to make sure you got the right friction angle because it's tangent phi prime there. And for the clay drained, we need our C prime and our phi prime. So these are our resisting forces. So SU times L for clay undrained, W cosine alpha tangent phi prime for sand drained, and C prime L plus W cosine alpha tangent phi prime for clay drained. So, so that's our resisting force, and that's our downward force. And then so our factor of safety is the resisting over the downward forces. Okay, so given these, find the factor of safety for this case, clay drained, okay, meaning that, you're going to use this one at the bottom, and you're going to use all these things here to get that. So it's 25 degrees, 40 degrees. There's my clay. There's the C prime's 165. Phi prime is 22 degrees. The saturated weight is 101 pounds per cubic foot. There's our dimensions. So plug them in and get the factor of safety. Pause the video here. Okay, if we plug everything in, so we're using these equations, and what do we get? Well, we get that L is equal to D over sine alpha, 18.9. We get H is this. We plug it in. We get 3.22 feet. We get the weight. Plugging it in here, we get 3078. We get our F down, W sine alpha, 1301 pounds per foot. Our resisting, F resisting, I'm going to plug it into this expression, and I end up with 4250. And so my factor of safety works out to be 1 over the other. That gives me 3.27. Okay, now what happens if we don't have that bedrock and we just have a slope here? So we have slope stability in clay. Then, so in other words, this is all clay here. Not too an unusual situation. Now, how can it fail? Well, and we don't have a bedrock to slide it on, so this is not a flat surface that it slides. What we observe is it actually follows a circle. We've seen this in our pictures. We get sort of a picture that looks like that, and we can get a really deep circle there. So we call these circles, this is called a mid-slope circle. Why? Because I'm looking at this point. That's in the middle of the slope. We call this a toe circle. Why? Because that point right there goes through the toe. We call this a base circle. Why? Because this one goes down and touches the bedrock down here at the base and comes out here. So it doesn't go through the toe and it doesn't go through the mid-slope. It goes way down there. So 3 different possibilities in a way of different failure circles. This is our shear plane. A shear plane is like that. Now, we have charts that help us with this one, so we're going to use charts. And so some terms are defined in the charts. ND is H plus D over H. Well, these are my H's and D's, so we use that geometry to get this ND to help us enter the charts, and I'll show you how to use the charts. For clay undrained, we get this term NS, which is called a stability number, but it's just whatever it's defined as gamma H over SU, sometimes written as gamma H over C, but we prefer the term SU to C. And if the slope is underwater, in other words, when I say the slope is underwater, if you know, the water level is up here, or the water, if the water is here, the slope is considered to be underwater. If we have that, then we're going to use, instead of the gamma, we're going to use a gamma prime, which gamma prime is gamma buoyant, which is gamma saturated minus gamma W. If we have clay drained, so again we have, remember, clay undrained, clay drained, and this is only for clay, so this only works for clay here. And then our NS is going to be gamma H over C prime. Remember, we have our failure envelope where this is C prime and this is phi prime. You have to know this. This is sigma prime and this is tau. And if you have so this is our NS, which we're going to use to enter the chart. If the slope is underwater, then it's gamma prime H over C prime, where gamma prime is gamma saturated minus gamma W. Okay, so these are the terms we need. We need an ND and we need an NS. We can enter our charts. Here's the chart, and what do we have? We have this, these are small NDs here, and this is our NS. So we're going to use those in the chart. This is the beta. This is our slope angle. And this is for soils with phi equals 0. Phi equals 0 is what? This is clay undrained. So this is really important. This is the way it's written here. So just to let you know, this is clay undrained only. So undrained, there are no space here. But so know that. Don't use this for other ones. That's for this one. And I'll just note that when the factor of safety is 1 for these slopes. If a point falls on the line, the factor of safety is equal to 1. It means it's just about to fail. So that's how we're going to use this chart. And then there's another chart here. This is for clay drained. So this is important, and again, slopes that fall on the lines have factor of safety 1. And again, I have beta here, and I've got my NS here, and I've got, now in this particular case, though, I have just the phi primes over here. All my phi primes. Okay, so again, this is cohesion and friction, another way for them to say clay drained, because I have a C prime and a phi prime. Okay, so this is clay undrained, and here's my slope. I want to know what the beta is. I want a factor of safety 1.3, find the maximum beta. Okay, here's my SU is 500 PSF. Now, so there's the details. Now, first thing I'm going to give you a hint on how to solve this problem is because I have to have a factor of safety of 1.3, how do I put that into my problem? Well, typical way of doing that is to reduce the actual shear strength in your calculation. So you actually have 500 PSF, but when you do the calculation, you slip in the factor of safety by dividing by 1.3, the factor of safety that you want. So if you want a factor of safety of 2, divide by 2. But so the way to input the factor of safety, so just change your SU to this, and then you want to use, this is the correct chart, so use this chart, and just give it your best shot here on how to use these, see if you can figure out how to use these charts. So pause the video here and do this problem. Try to find, you want to find the beta. What's your best, what beta can you use? Okay, so here's how to use the chart. Like I said, we use SU as 500 over 1.3, which works out to be 385. We get our ND, which is our H plus D over H. Well, what is that? That's going to be the, this is our D. Our D then is what? This is 60, so that's 20, so the D is 40 feet. And so when I do my h plus d over h, I get 3, 20 plus 40 over 20. I got my SU of 385. That gives me my stability number. NS is going to be the gamma H over SU. So I get it as being 6.49. And then that means what? How do I do this? So I have on my y-axis the NS, which I go at 6.49, and then I use my curve that is ND equal 3, and then I get that point, so I go over here, go the right curve, then I come down and I get my beta, I get a beta of 11 degrees. So to get that stability, I need beta of 11 degrees. Let me just show. So this is the way it is. The way you read the chart, you got an ND here of 2, you got an ND here of 4. So I don't have a 3. So I got to sketch in a 3. And so I sketch in a 3, ND equals 3. I've got my, I go to my 6.49 over here, then I come down. And notice these are going backwards, 0, 10, 20. So I get about 11 degrees.